Hello and welcome to my presentation. My name is Christian Schweikert and I'm a PhD student from the University of Stuttgart at the Institute of Electrical and Optical Communications Engineering. I'm very pleased to present you an improved phase detection in on-chip refractometers. First of all, I will start my presentation with a motivation and explication of the relevance of the proposed phase detection system. That overlaps with the introduction of the interferometers I have investigated and improved, and the improvement itself bases on a 90-degree hybrid, which follows as the next point, and last but not least, I will conclude the whole presentation. So, biosensing is a very topical and research subject area for an accurate analysis of molecular decompositions of substances under test. Especially in point-of-care diagnostics, the integration of such a system on a microchip is in demand. And one subgroup of the biosensing represents refractometry, so the measurement of refractive index. For instance, this is used for concentration determinations. And in combinations with functional gladings, the sensitivity of such an refractometer can be aligned for desired substances. And here you can see several approaches a refractometer can be realized. It can be based on surface plasma resonance-based sensors, optical ring resonators, photonic crystals, and on interferometers. And the focus in this presentation is set especially on interferometers. More precisely on Mach-Zehnder interferometer and on bimodal interferometer. So their working principle is explained on this slide here. You see here a common setup of a Mach-Zehnder interferometer. The incident signal is split by a 3 dB coupler into two waveguides. In each waveguide a fundamental mode propagates. One waveguide is surrounded by the substance under test that directly affects the phase velocity and thus the phase of the propagated signal. Therefore, both signals here have a moderate phase difference. An outgoing 2x2 multimode interferometer brings both signals into interference, and dependent on the output interference pattern, this resulting phase shift can be read out according to this plot here. Observing only one output, you can calculate the resulting phase shift with this formula, and considering both outputs, you can use this here. Both arguments of the equations follows the cosine function, but latter has the advantage that it's independent of the input power and therefore it's independent of input power fluctuations. 3 out represents the resulting phase shift if you have a substance under test on your Mach-Zehnder interferometer. With respect to a phase shift and well-known phase shift from a resulting of a well-known material with defined refractive index, you can calculate the total phase shift. And this total phase shift is directly proportional to the change of refractive index. So the difference between the unknown refractive index of your material on the test to the well-known refractive index of your reference material. A more complex interferometer represents the bimodal interferometer. Instead of the usage of two locally separated signals here, you use only one common bimodal waveguide. Therefore, this system here can be realized in a more compact way. In this system, two different modes are excited in a bimodal waveguide. So you see here in green marked the fundamental mode and brown marked the mode of first order. They are orthogonal to each other and have different phase velocity. The substance under test here affects both modes in a different way. With the presented butt coupling at the output, the modes interfere, and the subsequent phase detection is the same as presented for the Mach-Zehnder interferometer. So this formula is also valid, however, they are only valid for the Mach-Zehnder interferometer or for the bimodal interferometer if losses are neglected. But in reality, the losses aren't neglectable. I introduced here the transmission coefficients. If you operate with a monochromatic input laser source, these transmission coefficients have to be known. Without them, the phase cannot be detected due to this dependency of the phase calculations here. That's one challenge. Another challenge shows the so-called ambiguity here. So if you measure, for instance, with a monochromatic laser, your transmissions and want to calculate your output, so you can't distinguish between these 2 points. So you have ambiguity. So you are limited in such a range here, where you have an unambiguous phase detection, or here, but you can't use the whole range over 2 pi. So commonly, the interferometer is aligned such a way that it operates in that ranges here. So the minimal and maximal desired measurable refractive index changes set the boundaries for this operation area, and so you are unambiguous. But the problem is here that we are strongly limited in sensitivity, so the response of the transmission dependent on the refractive index changes. You want a high sensitive operation normally. Therefore, an additional interferometer can be used that shows a more sensitive behavior that can be reached with a larger sensor region, for instance. In this graph here, the interferometer length of the green marked curve is 8 times the blue one. So this point, this point, this point here, the slope is very high and therefore it's very sensitive. However, there are still ranges in the graph that has a slope around 0. So consequently, a change of the refractive index results in a small change of the measured transmission, and therefore the sensitivity is quite small and you are limited. So the phase detection of commonly used interferometers shows challenges due to its unknown signal losses, ambiguity, and sensitivity. To overcome or improve these problems, a 90-degree hybrid is proposed. That's a simulated design in the 220 nanometer SOI technology for a wavelength of 1550 nanometers. The simulated excess loss is 0.08 dB, and the simulation environment is from waveform prop. The lower picture here is a cutout from this layout, so it's true to scale. Usually the length of the sensor is several millimeters long, reaching a high sensitivity, so the relative size of the 90-degree hybrid is quite small. And here a first analytic model shows the working principle of the system. You see the scattering matrices of the power splitter, the transmission through the sensor area, and the 90-degree hybrid. With that formula here, the electric field vector of the output can be determined. That vector consists to the complex electric field amplitudes of the fundamental modes per output. So solving the equations and calculating the output powers and refer them to the total output power, the following equation system here holds. And here they are visualized, and you clearly see the 90-degree behavior. These curves here are simulated with waveform prop. And for the plot, the transition coefficients are set to 1. With further calculation steps, you can emerge this equation system here to that equation. So solving to the phase shift delta phi, you get this formula. And to extract desired phase shift, you have only an equation that depends on the measured output powers P1, P2, P3, and P4, without any unknown variable as the transmission coefficients. So one further advantage is that you have an ambiguity over 2 pi, and I think it's very good to explain in this graph here. So For instance, you observe output 2 and output 3, and you measure transmission of 0.25 each. So you are in this point or in this point. So if you want to extract a phase shift here and you observe this both outputs, you can say, okay, is this point or this point? But now you have the possibility that you also have a look at output 1 and output 2, and here you see, okay, you can clearly say which phase shift results. A next point is that you always operate in a sensitive bias. And for this explanation, we have a look at this phase shift here, for instance. If you measure output 1 or output 4, you have a slope in this operation range around 0, so it's insensitive. However, if you at the same time have a look at the output 2 and 3, you operate in a high sensitive range. So you can have over 2 pi always a sensitive operation. The working principle can be also adapted on a bimodal interferometer. So here you see a proposed system. It's a little bit more complex. The bimodal output of the sensor region is here the input for the phase detection system. Before the both modes were brought into interference, they have to be separated with the peak mode converter here. Its functionality you can see here by ONT. The fundamental mode passes the mode converter with a simulated excess loss of 0.09 dB to the middle point, whereas the mode of the first order can be extracted from the upper and lower part of the mode converter with an excess loss of 0.22 dB. And their module phase shift here of these both signals is 180 degrees due to the asymmetry of the mode of first order. So the modes here are splitted, and a subsequent 2x2 multimode interferometer splits the self-image multimode fundamental mode into 2 signals with a module phase difference of 90 degrees. So the 4 guided signals here can be brought now into interference with the shown 2x2 MMIs. And here these 3 2x2 MMIs are identical. They all have an excess loss of 0.07 dB each. The simulated excess loss of this whole phase detection system is 0.26 dB. So now you can extract the phase shift. You see here the 90 degree behavior, the curves also simulated from wave. Compared to the 90 degree hybrid of the Mach-Zehnder interferometer, the output 2 and 4 are changed. Take this change into account. The presented formula from the Mach-Zehnder interferometer for the phase shift extraction holds for this system too, with an additional constant phase offset. So in conclusion, I presented a phase detection system that enables an unambiguity over 2 pi, that enables an operation in a sensitive point, that is independent against input power fluctuations and unknown mode losses, and have a high efficiency. For example, in the Mach-Zehnder interferometer, the simulated excess loss is 0.08 dB, and in the bimodal interferometer, the simulated excess loss is 0.26 dB. These arguments are for a single wavelength operation. So that was my presentation. Thank you for your attention.